Welcome back to the channel. Today we're diving into one of the most ambitious and groundbreaking projects on the planet, the International Thermonuclear Experimental Reactor, or ITER for short. It's not just a work of engineering. It will mean that man could finally gain access to almost infinite clean energy, a total change in the landscape for the future production of energy. Join us on this journey to learn what ITER really is, what its current challenges are, and how global collaboration is driving hope for its success. ITER is commonly called the largest construction project in the world. Located in the French countryside, an hour's drive to the north of Marseille, the construction from the outside looks like an equally large set of conventional industrial buildings. However, inside those buildings, scientists and engineers are working to recreate a process that fuels the sun on Earth. If experiments are conducted successfully, this offers an unlimited supply of clean energy capable of dealing with humanity's biggest problem: how to power civilization sustainably. Before going further into the details on ITER, one should first grasp the importance of nuclear fusion. Even though fission indicates the breaking of atoms to release energy, a process on which current nuclear reactors are based, fusion, on its part, means a process of forcing atomic nuclei to join. But it releases an extraordinary amount of energy, 4 million times greater than burning fossil fuels, without releasing ecologically toxic greenhouse gases. The waste produced in nuclear fusion is not long-lasting nor radioactive. Accordingly, in principle, the peril of a catastrophic meltdown is also lower than in fission. Nuclear fusion is a fundamental process. In straightforward words, it is a process powering the sun and other stars. In the center of the sun, the nuclei of the hydrogen collide with such terrific heat and pressure that they actually stick together to form helium atoms and release vast amounts of energy. The biggest problem on Earth has been reproducing that phenomenon under controlled conditions. To effect the fusion, one must reach a temperature of about 10 times that registered in the core of the Sun, 150 million degrees Celsius. At such tremendous temperatures, hydrogen gas only turns into plasma, the superheated state of matter in which electrons are stripped from atoms. The answer to trying to attain controlled fusion on Earth is within a device called Tokamak. A Tokamak apparatus has a toroidally shaped chamber in which magnetic solid fields create and confine the plasma. These magnetic fields are produced by refrigeration appliances to the adherents, called superconducting magnets to nearly absolute zero, a few degrees above -273.15 degrees Celsius. Inside the tokamak are hydrogen isotopes like deuterium and tritium, heated until they turn to plasma. Thereafter, magnetic fields are arranged so the plasma is confined long enough so that the two nuclei, as the particles collide, will fuse and create energy. This is a very difficult job to achieve with machine building, and that's where ITER proves to be an absolutely important mission. The ITER tokamak is the largest and most complex fusion device ever designed and built. More than 1 million pieces and 10 million different components must fit together with the tightest tolerances. Clearly, it shows ITER to be an international venture. Components come from several parts of the world. In total, 35 nations are involved with building and running ITER, so it is one of the most significant international collaborations of countries acting together in history. The idea for building ITER began in the 1980s, when Mikhail Gorbachev, representing the Soviet Union, and US President Ronald Reagan proposed an international fusion initiative. In this era, as the Cold War was coming to a close, the two leaders saw new energy for all humanity. In 1986, the counterpart to the formal launch of the ITER project was those subsequent years as more states joined in, including members of the European Union, Japan, China, India, South Korea, and, of course, Russia. It is at this moment that ITER, with the choice of the best location in France and the necessary infrastructure, began construction in 2010. Since then, thousands of scientists, engineers, and construction workers have applied their efforts to implement the project. The very technicality of a tokamak meant it was designed to overawe the user. The sum of its parts, from the superconducting magnets to the cooling system, calls for sophisticated technology and fine engineering. For example, the cryostat, the largest stainless steel vacuum chamber ever built in the world, was fabricated in India, pre-assembled, and then shipped to France, where it was finally assembled. It surrounds the tokamak, allowing the superconducting magnets to cool to the intended low temperature. Another important section is the actual assembly of the tokamak. Functional parts first go to an assembly hall, where the highest degree of preparation is carried out before they're taken to the actual building premises where the tokamak stands today. Genuine construction becomes exceedingly delicate and must be carried out impeccably, as otherwise the slightest mistake would mean a total breakdown of the system. For example, all of the vacuum components must be leak-tight, since even a tiny leak will disturb the tokamak plasma. That's really an impressive scale. The tokamak has a weight of over 23,000 tons and has 39 buildings and technical areas on site. In fact, cooling towers are used with waste management systems and even cryogenics plants that produce liquid helium to cool magnets. Then there is the control room, from where scientists will control and monitor how thermonuclear reactions proceed. No other project is equivalent to the ITER project in terms of the international cooperation shown, either directly or inferentially. Financial and technical contributions toward the realization of the project come from all participating countries. For example, Europe pays a little less than half of the construction cost, while the other rival partnering Hemi countries also pull their weight. Even the workforce is representative. Around 15,000 employees from 90 countries join forces of different cultures, languages, and fields of expertise to achieve a specific goal. However, the realization of ITER has been marred with the list of the following problems. Running both behind the program and over the budget, the project was so complex and demanding toward every detail of the construction process. Some of the major problems include the cracks in the cooling pipes and the misalignment of components within the walls of the vacuum vessel. These have brought time-consuming repairs and continually delayed the project's timeline. All these problems notwithstanding, the atmosphere in the ITER organization for the future is optimistic. The design, manufacture, construction, transport, assembly, and installation activities represent over 3/4 of the work. The next step would be to light the assembled machine, which will be done in first plasma, heating the hydrogen fuel in the tokamak to form the plasma at the desired temperatures. This would practically show that large-scale controlled nuclear fusion works. But ITER goes indeed beyond just achieving fusion. It is the realization of burning plasma, fusion being carried to a self-sustained state, releasing energy on balance without needing substantial extra heating. If ITER achieves this, a significant step will be completed on the final goal of developing clean energy. There is, however, one point to mention. ITER is an experimental installation and will, therefore, not be a power plant connected to the grid. Instead, the experience derived from ITER will be used to propel the future generation of fusion reactors that could someday provide power to cities worldwide. Nuclear fusion potential is vast and practically unlimited, while fossil fuel resources deplete and heat the planet. As it comes to safety, the possibility of it resulting in a disaster would be much less compared to nuclear fission. Mainly, no meltdown events can take place, the fuel is widely spread, possibly to be taken from water-hydrogen isotopes like deuterium and tritium. In addition, fusion waste from the reactors creates no long-lived radioactive waste, making them much greener. Indeed, it is only when one considers the future that it is clear ITER forms the basis of genuinely shaping this new era of energy development. It is no less a sign that humanity can pull off the near impossible if and when it decides to rise together to the occasion. In the meantime, despite such a great sea of pending challenges, astonishing advances come with them. The experience from ITER will be invaluable as it forges ahead in providing insight into the potential of nuclear fusion and, very importantly, an end to the growing demand for energy in the world. In summary, ITER stands for International Thermonuclear Experimental Reactor. Yet one more superlative for the leading landmark in scientific and engineering achievement. It is a project whose stakeholders range from over 35 nations, with scores of experts, and it employs some of the best technology on Earth. As we push the possible limit, ITER promises a brighter future, safe, clean energy. Thank you so much for watching. If you liked the video, like it, leave a comment, and subscribe to our channel if you want to be primarily kept in the loop. We would be happy to read your comments on this vision of nuclear fusion as a way out of an energy crisis. See you in the next video.